I think it's time to get started. Hi, everyone. I'm Jessica at Men&Mice, based here at our HQ in sunny Iceland. I welcome you to Men&Mice's first 2020 webinar, which is an update to the current state of affairs with encrypted DNS. This year, Men&Mice is celebrating our 30th birthday as industry-leading experts in DNS, DHCP, and IP address management solutions. If you're interested in learning more about our unique approach to DDI and our market-leading overlay solution, please send me an email at sales@menandmice.com, and I'll get back to you right away. But that's not why we're here. Today's main event is a webinar led by Carsten Strotmann, who has several decades of experience working with issues surrounding networking, DNS, and IPv6. He's been consulting with Men&Mice for over 20 years, and you can find him online via his website, the URL of which he'll share in his slides. Before we begin today's main event, some basic ground rules. We encourage lots of questions, but we ask that you send these questions via the Zoom chat function instead of interrupting Carsten. He's going to go just straight through. You can send them either directly to me or publicly to everyone, and I'll collate the questions at the end and facilitate a Q&A session. So, we'll also host a question box online where you can ask further questions if needed, and we'll send the link to that as soon as possible. But without further ado, please, Carsten, take it away.
Thank you, Jessica. Hello, everybody. Welcome to today's webinar on encrypted DNS, episode 2. Now, this is an update on a previous webinar that I did 2 years ago, and it is all about DNS encryption and the current state. So we will talk about DNS privacy and why there is a need for DNS encryption. We talk a little bit about the different implementations of encrypted DNS and the current status. And then we will dive deeper into Oblivious DOH, which is a version of encrypted DNS that is currently deployed by Apple in their devices. So Jessica already told you about me. I work for about 20 years with Men&Mice, and my main topics are DNS and DNSSEC, DANE security, DHCP, and IPv6. And if I find time, I'm hanging around at RIPE and IETF meetings. So why do we need privacy in DNS? In the recent years, the IETF, the people who do the internet standards, they have expanded the DNS protocol with new privacy features. And DNS-over-TLS and DNS-over-HTTPS, both which we will discuss in this webinar, are part of that. There are others, like QNAME minimization and eDNS padding, which we have talked about in previous webinars, and I won't go deeper into these this time. If you are interested about these, please look online and on the Men&Mice webinar page or on the Men&Mice YouTube channel, and you'll find the webinars there. So a study presented at the IETF meeting in 2019, in summer 2019, found that around 8.5% of all networks worldwide intercept the DNS queries, meaning a query coming from a client will be intercepted, something will be done with it, and then it will be sent upwards to the actually resolver that the client had addressed. The number is much higher in China with 27%, and it might also be higher in other countries. But overall, worldwide, it's 8.5%, which is still a high number. The same researchers found out that today, most of these queries are answered without being changed. However, the situation might change because once the infrastructure is in place, and it seems to be in place, it's trivial for the people who do this to also change the answers. And that can lead to censorship, that can lead to attacks and malware to be distributed and other stuff. So encrypted DNS is about preventing these kind of man-in-the-middle attacks. So what do we have? Because encrypted DNS brings more different versions of the DNS protocol into the game, we need to have new terminology for that. And we have new abbreviations for the different protocol implementations. We talk about DO53 when we mean the classic DNS, which is the old and trusted DNS that we have used for the last 40 years, DNS over UDP and TCP port 53. A little bit newer is the DNS over TLS, which is the first encrypted DNS protocol that has been standardized. Later on, there was then DNS over HTTPS, which is called DO. And in the future, we might have DNS over QUIC, where QUIC is a new transport protocol currently standardized inside the IETF. It's originally coming from Google, and they are using it today for their Google search page and for YouTube. So if you use the Chrome browser or an Android phone and you visit YouTube, you are already using QUIC for the web. But QUIC is a general transport protocol, and also DNS could be used over QUIC. And the last one, DNS over cloud, is not really a transport protocol, but it is the notion that people don't use their own local DNS resolvers anymore. Instead, they use some service providers in the internet, in the cloud, something like Google, Quad9, or Cloudflare for the DNS name resolution. So very short about the main protocols we see in the encrypted DNS space. The first is the DNS over TLS, which is just the normal DNS wire format, just transported over TCP and then wrapped in TLS for security. It runs on a dedicated port, port 853, and it gives us encryption and authentication, meaning nobody can look inside the data, nobody can see what we ask and what the answer is. And also authentication means that the client can be sure that it is talking to the real DNS resolver it wants to talk to, and not to a man in the middle that intercepts the traffic. And the second big one is DOH, DNS over HTTPS, which is the same DNS traffic, but this time it's wrapped first in TCP and then in HTTP, the same protocol that we use to view the websites. And the benefit of that is that it gives us, in addition to encryption and authentication, it gives us cloaking, meaning that we can hide the DNS traffic inside the web traffic. Someone looking from the outside cannot distinguish whether the data flowing between the client and the server is DNS queries or whether that is web traffic. And that makes it very hard to selectively just censor DNS and not break the web. What was interesting is that DNS over HTTP was standardized very, very quick. Normally it takes multiple years in the IETF from the first idea to the finished standards document, an RFC. This time with DOH, it started with an idea in November 2017 when the DOH working group was created. And then in the March next year, in March 2018, the work on the draft was finished. And a working group last call was started in April 2018. And a working group last call means the document is complete, and it will, and the working group is asking anyone out there if anyone has any objections against this protocol. And then it took another few months editing the document, getting all the typos out, until then in October 2018, RFC 8484 had been published. And this is less than a year from starting the working group until the standard was finished, and that is record-breaking speed for the IETF. So this also shows that there seems to be demand and also mighty players that are pushing this forward. What people see as a problem with this encrypted DNS is that because the traffic is now encrypted between the client and the resolver, it is impossible for network administrators to do network intelligence by looking at the DNS traffic. So here's a quote from the DOH-RFC saying that filtering and inspection systems that rely on unsecured transport of DNS will not function anymore in a DNS-over-HTTPS environment because they can't look inside the data anymore. Now, there are ways around that, but this is a concern of some security people. And it's always maybe a battle between the privacy and the security part. And we have to find some middle ground here. We have now two protocols for encrypted DNS, one being DOT, DNS-over-TLS, the other one is DOH. What are the differences here? DOT can easily be blocked because it's running on a dedicated port 853 TCP. Even in most enterprise networks, that port is blocked by default because enterprise networks have a deny all and permit only whitelisted ports policy. This is problematic for the deployment of DOT because it's today very hard to use DOT because it's very likely blocked and it wouldn't work. DOH, on the other side, is using port 443, which is the same port we use for web traffic. And that is almost universally open all over the world in any networks. So it can just travel through the same port as a normal web traffic. And selective blocking of just the DNS part of port 443 is very, very difficult, maybe even impossible. Another benefit of DOH is that it is easier to implement because it's built on HTTPS, and almost all programming languages have some HTTPS libraries that makes it easier for the developers to implement DOH. And the developers have experience in working with the web protocol. And lastly, DOH enables the developers to do DNS name resolution from an application level. They are not bound to the operating system and the functions the operating system exposes to the application. Instead, the application can use all the functions that DNS provides. There is a dilemma on how to deploy DOH, and that's brought up much controversy in the discussion around encrypted DNS, especially how Mozilla with the Firefox browser choose to deploy DOH. Because in order to make DOH really effective, you need to reach many, many internet users. You need to reach the majority of internet users. But the average internet user doesn't really understand the need for encryption of DNS. So it needs to be enabled by default without asking the user first. However, the way it is implemented in Firefox, it will be enabled without asking, but it will be defaulting to Cloudflare as the DOH service provider. And that creates a problem for privacy because now a huge amount of DNS requests are sent to Cloudflare, and that leads to centralization, and Cloudflare will see a lot of DNS queries that they haven't seen before. Now that might not be a problem because in some areas of the world, the users and the ISPs already sent the majority of DNS queries to a service provider in the cloud. But in other areas like in Europe, this is seen as a big problem. The ITF, the people that work on the internet standards, they currently discuss alternative ways for a client to discover secure and trusted DNS resolvers, and that is in the ADD working group, the Adaptive DNS Discovery working group. And in this webinar, I will present one option on how discovery can work. Now, the browser vendors like Mozilla with Firefox, they have built in certain checks in their products in order to be able to allow the network administrator to control the use of DOH. And one of these checks is the canary domain. A Mozilla browser, like Firefox, if it starts up, it will query for the name used application DNS.net. And if that domain name can be resolved, meaning there is a DNS response coming back with either an A or quad A record, then Firefox sees this network as being an unmanaged DNS network, and DOH will be auto-enabled in that network. On the other side, if the domain name cannot be resolved, that means it is blocked and the result is an NX domain or a no data answer, then DOH will not be enabled because this is a managed DNS network where the administrator took the deliberate step to block this domain. So this is an indication for the browser that DOH is not wanted in this network. So if you don't like DNS-over-HTTPS in your network for whatever reasons, what you can do is on your own resolver, you can deploy the use application DNS.net zone, DNS zone, like on a bind resolver or an unbound resolver, and keep the zone empty, because that will lead to an empty response on the query and disabling DOH. Now, this used application DNS.net domain name is something that Mozilla came up with, and the IETF is currently discussing and standardizing how this could be done across multiple vendors and across multiple implementations of DOH. In addition to the canary domain, Firefox, when starting up, is doing some other checks to detect whether it is a network, it is working in a network where content filtering is enabled, because enabling DOH could disable content filtering that is done via DNS. So it resolves the safe search variants of google.com and youtube.com to figure out whether they are in use. It looks on the operating system side on Windows and macOS, but not on Linux, to detect parental control applications. This is because, to my knowledge, there don't exist any parental control applications in Linux, only on Windows and macOS. And it does additional checks. For example, it looks if the Firefox browser has its own enterprise root certificates configured in the preferences. And if that is true, then there's very likely an enterprise policy configured. So it will not enable DOH automatically. Still, the user can go into the preferences panel and enable DOH manually. That is always possible. So what is the current status of DOT and DOH deployment? We already talked about the Firefox browser, and Cloudflare is the default choice there. And you can, as a user, select NextDNS as an alternative DOH server. And soon Comcast Xfinity will also be added to the list, and users can choose them. Mozilla started an automatic rollout in the US in February 2020, and that rollout is still gradually going on. On the Chromium browser side, DOH is enabled in almost all of them. That is, all the browsers that are built on top of the Chromium browser, the open source part of the Google Chrome browser. So we have that in Google Chrome, in Opera, Vivaldi, Brave, Microsoft Edge, and Bromide. But these are not automatically enabled, except for Bromide, which is a security focused browser, but in all the others, the user needs to go in some preferences and enable DOH in order to make that happen. And then DOH is auto upgrade, so there are no default cloud service DOH service that will be used. Instead, the browsers will probe the configured DNS servers of the operating system and see if they support DOH. But Google is also experimenting experimenting with adaptive DOH resolver discovery via DNS, which is very similar to the approach that Apple is taking, and which I will explain later in this webinar. On the Apple platforms, the Safari browser supports DOH and DOT in the coming versions of iOS and macOS that are due this fall, and they will also support the adaptive DNS resolver discovery that we will discuss later in this webinar. The latest builds of Microsoft Windows 10, the insider builds, which are kind of a beta version of Windows 10, they already have DOH enabled, and you see that here. This is a screenshot from the configuration panel where the Google DNS, no, Cloudflare DNS and Quad9 DNS are being filled in. Currently, it's only possible to put in IP addresses from DOH servers that are on a permit list in Windows 10. So you can't host your own DOH server, or you can't use any of the alternative DOH servers that are provided by privacy organizations around the world. You can only use the IP addresses of servers that are put in by Microsoft into the product. So Cloudflare works, Google works, and Quad9 works, and possibly a few others. But only the ones that are on the permit list. On Linux, we have DOT support in systemd resolved, and all the Linux distribution that come with systemd now should have that built in. However, DOT is not enabled by default. The user needs to go into a configuration file and enable DOT there. Then it is in opportunistic mode only, meaning if there is some lookup failure over DOT, it makes an automatic fallback to DNS53, and that makes it very easy vulnerable for a downgrade attack. And also there's no server authentication, so a man-in-the-middle attack is still possible, because systemd resolved doesn't check the TLS certificate coming back from the server. Systemd resolved allows global or per interface setting. Yeah, and it's not enabled by default. So on Linux, currently it looks quite weak. Luckily, there are third-party products that you can install from the repositories that implement proper DOT or DOH. One of them is the Stubby product from the good people from Internet Labs. On OpenBSD, OpenBSD being one of the Unix variants that have a focus on security, of course they have support for encrypted DNS, and that is implemented in the unwind daemon. It's also not enabled by default, so the user has to go into some configuration there. It supports automatic auto-update mode to the configured DNS server, DNS resolver coming from DHCP. It is also possible to put in your own DOT servers in the configuration file, and you can configure unwind to work in a strict mode where fallback to unencrypted DNS is not possible anymore. And the server is authenticated with the certificate, meaning there's a man-in-the-middle attack is not possible anymore. On Android, DOT is available and supported since Android 9. It's a manual setting, so the user needs to go into the network settings and need to enable secure DNS there. And it's an auto upgrade from the configured DNS resolver received over the network, or it is using the Google DNS with DOT as a fallback if the local DNS resolver doesn't support DOT, or if there's some connectivity problems. The biggest change this year is on the Apple platforms with Apple macOS 11 and iOS iPadOS 14. They now support both DOT and DOH, and either global in the operating system or in a per app or application setting. That also means that the setting in the application can be different from the global setting. So it could be that a global setting is set to use a local DOT server, and then one application has it hard-coded that it uses DOH to a different server. The operating system can learn the per domain DOH DOT settings via DNS or HTTP. That is part of the adaptive DNS over HTTPS. It's also possible to discover the encrypted DNS servers via DHCP or provisioning domains, or via a query to resolver.arpa over the classic DNS53. The different discovery methods are currently in active discussion in the IETF ADD working group. They are not standardized yet. Still, Apple has decided to already implement their versions of these. Possibly I expect that Apple will only use these for their own services like iCloud and the Apple TV and all the Apple owned services and backup services, and at this moment not for any other domains outside the Apple property. However, once it is standardized, I expect that Apple will open that up and it will work for all domains. So what is this adaptive DNS over HTTPS? The idea of adaptive DNS over HTTPS is that no party other than the client or the server can learn or control the names being queried by the client or the answers being sent by the server. So nobody in between should learn what is being sent, and also nobody in between should be able to make changes to the content. Only a designated DNS resolver, which is associated with the hosting content, should be able to read both the client IP address and the names being queried for privacy reasons, meaning that if there is a DNS server, or sorry, a DNS resolver that is associated with a company, then it's okay if that sees whatever is being queried in the IP address, because it is about a website that is run by the same company, and the web server will anyhow see what is being requested and from what IP address this is coming. So for example, if someone wants to go to the Men&Mice website, it is okay to expose that information to a Men&Mice run DOH server. Or if the client goes to an Apple website, it's okay if that information previously is being disclosed to a DOH server run by Apple. But however, it should not be disclosed to a DOH server or a DNS resolver that is run by some other party. Still, with the adaptive DNS over HTTP, clients should be able to comply with policies required by local VPNs or local enterprise networks. For example, local enterprise network might have an Active Directory deployment, and that Active Directory deployment will have a local namespace that is only valid for that network. And these names and these queries should not go out to the internet, should not go out to any third party in the cloud, because that would be leakage of privacy sensitive information. This this notion and this adaptive DNS discovery is being implemented by new DNS records. Either the HTTPS service record or the SVCB records. Now, these records are still in discussion in the IETF and they are not standardized, so you won't find them in your current bind or Microsoft DNS or Unbound server. In the implementation from Google and Apple, they are currently using DNS records from the private record space in DNS. If you see records with the name of type 65,000 and then a 3-digit number, that is a record from the private number space of DNS records, and that can be used for experiments. Still, both Google and Microsoft are using records from this type for their experiments and for their implementation in their products. Information about the DOH servers can also be revealed from a web server using the HTTPS alt service header that is coming back from a web server to a web client. There could also be a well-known URL, meaning if we want to connect to a service at Men&Mice, there would be a well-known URL, menandmice.com/.wellknown/DOH server, something like that, where there is a web page or a JSON document that can be downloaded, which lists all the trusted DOH servers. And it could also be through a local provisioning domain. Local provisioning domains is a very, very interesting topic, which we will very likely discuss in one of our future webinars. So the HTTPS service record is not only providing information about DOH, it's actually being invented to do something else. In the modern web, a web server needs a lot of information from DNS, which currently needs to be collected one piece at the time. So a client needs to ask for IPv6 addresses. A client needs to ask for IPv4 addresses. The client, in order to use encrypted SNI, needs to have the public keys for the web server, which are also stored in DNS. And when HTTP3 quick is being deployed in the internet, then we need also information what protocol level the web server is supporting. Does it support the old legacy HTTP 1.1 or HTTP/2, or does it support the new HTTP/3 quick transport protocol? If a client would collect all this information from DNS by its own queries, that would take a long time. And the HTTPS SVC record is now being created to allow the client to do one DNS request and get all information at once. The IPv4 address information, the IPv6 address information, the protocol information to connect to the web server, all the public keys required to easily set up a TLS connection, and other data such which trusted encrypted DNS resolvers could be used. Here's an example how an HTTPS service record would look like or could look like. Remember, this is still in discussion. It's not finalized. The standard is not finished. So here we see two records. The first one is kind of an alias, redirecting example.com to serviceexample.net. And then on serviceexample.net, we have all the information in there. We have the name of the server. We have the DO-ORI, which is the trusted DOH server. And then we could have public keys in there that will be used to encrypt the data being sent to that DOH server. So Oblivious DOH is an extension of DOH that is has been invented at Apple and is currently being discussed in the IETF. And this is what will be implemented or is implemented in the upcoming Apple products coming out this fall. And here's how that works. Now, there are a lot of players in this picture, and let me first explain what we see here. In the middle, on the top, we see a web server. And from that web server, the client being in the middle to the left, the DOH/DOT client, will later fetch a website. We have next to the client an IPv6 router that provides the client with a provisioning domain. On the bottom, below the client, we have a classic DNS53 DNS resolver that is being distributed via DHCP options. Next to him, we have a DOH, a DNS-over-HTTPS resolver that is published via an HTTP service record. This service, the DOH service, could be on the very same machine as the classic DNS. I choose here to have two icons to make it easier to grasp. And then on the right side, we have in the internet a couple of public reachable servers. On the top, we have the classic authoritative DNS server for vendor.com. Below that, we have a classic authoritative DNS server for example.com that contains the IP address information for the web server www.example.com. And then we have two DOH servers, one DOH-example.com, which belongs to the same organization that runs the authoritative server example.com. And we have a cloud service DOH called DOH example XYZ. And both the DOH servers are DOH or oblivious DOH targets and oblivious DOH proxies. Now, in the beginning, the client wants to know whether there is DOH server in the local network. So after receiving its IP address via DHCP and after receiving its classic DNS configuration via DHCP, it sends a query for an HTTPS service record to the domain name resolver.arpa. Resolver.arpa is a special domain name that is only valid in a local network. So it will never be resolved in the internet. The root name servers or the .arpa top-level domain servers don't know what to do with that. It's something that a local resolver should resolve. The answer is coming back from the local resolver telling the client, hey, yes, we have DOH in our network. Here is the URL that you can use to reach our DOH server. And that is the DOH server that is just right of the DNS resolver that is answering. The client also gets information from IPv6 router advertisements, which contain a provisioning domain information. And that provisioning domain information will then also give the DOH client information where to find the DOH server. So there are multiple ways to get that information to a client. If a client receives the DOH information from a router advertisement, it will verify that information by making an HTTPS connection to that DOH server, because the provisioning domain information in the router advertisement is not authenticated. So it could be forged, it could be spoofed, in order to make sure that there's really a DOH server with a proper certificate, and whether that one is really responsible for certain domains, it's asked with HTTPS. And when that is finished, then our client likes to get some connection to the vendor of the client machine. For example, if that is an Apple machine, it might want to make connection to the iCloud. So it asks via classic DNS for an HTTPS service records for the vendor.com. And the answer in that response is, also the data in that response is a list of vendor-approved DOH resolvers and proxies. And in this case, it includes DOH example XYZ, and it also includes DOH example.com. So both proxies that we see on the right lower side are approved by the vendor itself. Now, this response coming back should be secured by DNSSEC so that it couldn't be spoofed, and that the client can be sure that this is really an answer coming from the vendor and the list of DOH servers are really approved by that vendor. Then the client might ask one of the listed DOH servers and ask, hey, server, for which domains are you the designated DOH proxy or target for? So it asks again for an HTTP service record for that domain towards the DOH resolver. And the response here is the list of the names it is responsible for. And it includes also a public key, the public key for DOH resolver. And that public key is later being used to encrypt the query to that resolver. So now our client wants to go to the website. So it needs to know the IP address of www.example.com. It now knows that for example.com, it has this list of designated DOH servers and proxies in the internet, and it is selecting DOH example XYZ as the proxy to use. So it encrypts the query with the public key from DOH-example.com, but sends the query to DOH-example XYZ. Because it's encrypted with the public key, and DOH-example XYZ doesn't have the private key that matches that, all that that proxy server sees that there is a request coming from the IP address of the client, and it should be forwarded to DOH-example.com, but the first hop doesn't know what the content of the query is, doesn't know what has been asked here. Now, this is very similar to onion routing. So if you have looked at the Tor network that is used for secure VPNs all over the world, it works quite similar. So it also does multiple hubs, and the first hub does see the IP address, but it doesn't know the content of the communication. And the further hubs don't see the IP address of the client, but they see parts of the content of the communication. Same here. DOH example XYZ then forwards the request to DOH-example.com, which is the server in the middle. And that one has the private key that matches the public key, which has been used by the client to encrypt the content. So that server doesn't know where the client is, because all it sees is that this query has been forwarded by DOH-example XYZ, but it knows, oh, this is a query for www.example.com. And it now unwraps the encryption, creates a classic DNS query, and sends that onward to the authoritative server for example.com, which is above. That authoritative server will just send back a classic normal DNS response to DOH-example.com. And because it had the public key of the client, it will encrypt now that information with the public key. There is an error here in the slides. It says encrypted with client's private key. That's wrong. It's the public key. Yeah, because the private key should never leak the client. So it's encrypted with the public key that was in the query. And it is then forwarded back to DOH-example XYZ. Example XYZ doesn't see the content, doesn't see the response. All it sees that this should be forwarded to the client. It knows about the client because it has an open session for this name resolution. So it gets a response back, and it sends the encrypted response back to the client. The client has the private key that matches the public key, so it can encrypt the response, and now it knows about the IP address of www.example.com. And then it uses a website request to that web server. Here, because it's a very modern client, it's using already HTTP3, quick to do that. And in the response from the server, there could also be additional information. For example, there could be an HTTP alt service header coming with this response that then lists additional DOH servers that can be used for this website, in addition to the resolver that we already know. So over time, a DOH client will learn more and more about the infrastructure in the internet. They will learn about the domain names and which servers are the trusted resolvers for certain domain names. And because that is all DNS, it will have time to live attached to it. And that time to live will determine how long this data can be cached. So this concludes my webinar for today. Jessica, do we have any questions?
Yeah, actually, thank you, Carsten. We do. Let's look at a few of them here. Yeah, so does Bind 9 support DNS over HTTPS or DNS over TLS?
Not at the moment. The current version 9.16 doesn't support either of them. But I see the people who do the bind name server, they are actively working on implementing DOH and DOT. To make that happen, they had to upgrade the network layer in the bind code. So they made it more modern. They ripped out old stuff, and they already did that in 9.16. And the plan is to have DOT and DOH with the release of bind 9.18, which I don't have the roadmap here, but I think, if I remember correctly, that is due in early 2021. So early next year, we would see that.
Okay, okay.
Oh, sorry, one more.
Uh-huh.
Even though bind doesn't support DOH or TOT at the moment, it's possible to upgrade any DNS resolver. So no matter what product or vendor, bind, unbound, Microsoft DNS, whatever, with a DOH proxy. And there are many different proxy products that can be used. For example, there is a lot of open source products that are on the list. Here on my question slides, there is a link to links and resources. Let me click on that. Here we have a longer list. And this is on my website, DOH defaultroutes.de. And when we go on the main page of that website and go to DOT/DOH implementations, it has a long list of implementations for these protocols. And one of them is here, the DNS dist, which is from the Power DNS people, which is a DOH and DOT capable load balancer. It's open source, and you can put that in front of any existing DNS server without changing anything to that existing server. You don't need to change the configuration. You don't need to upgrade the software. You just put another component in your network, and then you have your existing service, DOH and DOT enabled. And that's a very easy way to do that. Also, I know that commercial DNS load balancer vendors also support this. So for example, load balancers from the company A10, they support DOH and DOT offloading, and you can put them in front of your existing resolvers to provide DOH and DOT to your network.
Okay, that's great. We have another question here that says, should I deploy DOT in an enterprise environment?
Yes, I would say yes, because I think encrypted DNS is here to stay. It will not go away. And enterprise administrators have actually two choices. Either they ignore encrypted DNS, and then there's a risk that the products that they have in their networks, the browsers, but also increasingly the operating systems, they will use DNS over TLS or DNS over HTTPS. And if there's no local resolver that supports these new technologies, they will go to the cloud. And that makes the administrator blind for the DNS requests that happen in their networks. If the administrator deploys a DOH or DOT resolver in their network, at least they see the unencrypted queries at the resolver. They don't see it on the transport, but they can look at the logs, or they can have some monitoring on the resolver itself. And at least they can have security mechanisms like response policy zones or other filtering mechanisms there. So I would say yes.
Okay, that's great. So I think we're going to wrap up now. If you stuck around to the end, well, that's great. And we thank you so much. I saw so many engagement within the chat box, people answering each other's questions and getting to know each other. That was really great. We'd like to remind everyone that today's session was recorded and will be placed online along with a question box. So you can come back, enjoy the webinar again and again, or share it with your friends or colleagues who also may want to watch. If you'd like to learn more about DNS, Men&Mice offers a 1-week DNS deep dive training. And we also offer consulting for all of your networking needs. So if you want to learn more about that, you can go to the Men&Mice website at menandmice.com to learn more about. And of course, check your inbox in the coming days for all the links to this webinar and more. And to wrap up, thank you again, Carsten, for this webinar. Thanks to everyone who attended and for such great enthusiasm. We always appreciate your participation and support. Until next time, guys, have a great day.
Thank you.